Hello, everyone. Good morning, or afternoon, or evening, depending on where you are, because we have worldwide participants in the course. Pleased to continue with the live sessions throughout the summer. Episodically, we'll try and vary the day and time so that different people can make it. Um,
Explain the Udemy problem. I have to log back.
oh, there was a
Next time
Udemy
we'll use the
Udemy issue was apparently that they've made changes to their system such that you have to log out and then back in for the system to work. So Udemy we had a problem with last time, but it's apparently as simple as logging out and then logging back in. So today we're using Blackboard and then capturing it on Google Plus, and we'll post on YouTube as usual. So pleased to be able to answer questions. The whole course, of course, is fair game and open at this point because the staged portion of the course with a different topic released every week is over. All the material is live. As I hope you've gathered by now, astronomy is making enormous strides in some important areas, but there are always more questions than answers, which is really why research is fun. So I welcome all your questions.
Okay, so the first question for today is, what is the difference between the Lambda CDM model and the Freeman equation?
Okay, Lambda CDM is kind of a jargon word in cosmology, shorthand essentially for a cosmological model that involves cold dark matter, the cold adjective there referring to the speed of the hypothesized subatomic particle at the time when energy and particles were equally dominant in the early universe. Cold therefore means subrelativistic, so that's an attribute of the dark matter particle. Lambda referring to Einstein's cosmological constant, and so that's just a reference to dark energy. So Lambda CDM is essentially a cosmological model with these two dominant ingredients, dark energy and dark matter, as we observe the universe to contain by astronomical observation. And that seems to be the universe model that we live in. The Freeman equation is something different. The Freeman equation is actually much more general. So think of Lambda CDM as the particular flavor of cosmological model that matches observations and includes these dominant components, dark energy and dark matter, with normal matter the minority of the three components. The Freeman equation is a way of solving general relativity for an expanding universe. And so it's the sort of general solution of Einstein's field equations for the cosmic situation. So it's a very general tool, and you can solve the Freeman equation in different ways. It's the dynamical evolution of the size of the universe over cosmic time. And it's part of the standard apparatus of cosmology that students, advanced undergraduates and graduate students in astronomy just learn how to solve the Freeman equation, how to manipulate it, how to play out how space expansion evolves over time with different ingredients in the universe. So it's the sort of generalized form of cosmology, whereas Lambda CDM is the specific flavor of the universe we think we live in.
So Pete has a really great question and comment. He would like you to comment on the latest with regard to the Kepler Space Telescope and potential in the near future to replace any lost capability.
Yeah, we've had a lot of good news and excitement in astronomy, and Kepler's problem was a huge piece of bad news, just unanticipated. Basically, Kepler has some redundancy. All spacecraft have redundancy in terms of how they point at astronomical targets. Kepler, as you know, is staring at one region of the sky and just staring for years and years and years, taking data every 6 minutes on roughly 150,000 stars, looking for eclipses, looking for transiting exoplanets. To do so, or to do any of these type of observations, it needs to point rock steady in the sky, and it uses reaction wheels and gyroscopes to do this. And Kepler, as most science missions, including Hubble Space Telescope, which has its own problems with gyroscopes, has redundancy. There's one extra, pointing device compared to what you need. But Kepler had a serious problem where it lost its fine pointing capability, and really to protect the telescope, because you can't have it wandering around in position on the sky, for instance, potentially pointing at the sun, and with the shutter open, that would kill the detectors. So you can't have a telescope that doesn't know how to point, and also you can't do your science. So Kepler is hamstrung at the moment, and it's been shut down for science operations. The mission controllers are not saying very much right now. They're being cautious. A mechanical device that's supposed to rotate freely is not rotating freely. It seems to have been bound. It's binding in some way that's not understood. They're obviously going to go through a series of processes to try and free it or make it work as it was originally intended, because this is not a mission that can be serviced. There's no way to fix it with astronauts or any other robotic rescue mission. The rescue mission essentially would cost as much as the Kepler satellite itself, which is why that's not contemplated. So there's sort of just a hope, and really it's hard to estimate the level of that hope, that the engineers working from the ground can issue enough commands both to understand and diagnose the problem and, reverse this issue where one of the critical pointing elements is not functioning normally. And it's going to take them several months to do this. So NASA sort of told everyone to not expect a quick fix here. It could be, they gave about 3 months as the time scale for potentially fixing it, or really deciding that it can be fixed. Okay, well, that was a long introduction. What does this mean for the Kepler mission and its goal of finding Earth-like planets? It's a serious but not fatal problem. I think the unfortunate thing is that Kepler, which has succeeded, enormously in its design, did have one problem. As the mission proceeded and Kepler clearly was detecting transits, it turned out that the astronomers and the mission scientists had slightly underestimated the amount of noise present in the measurements of transits. And that meant, playing out in terms of their science goals, that it was taking them longer to get to the detection, say, of a true Earth-sized planet or below Earth-sized planet than they'd anticipated. There was no problem because the data was still beautiful, and in a sense, Kepler succeeds just by piling on the observations, taking the same image essentially every 6 minutes. And so a year or so ago, NASA happily extended the mission, the time frame of the Kepler mission, by 3 years, which would accommodate this issue of the data not being quite as high quality or having larger noise than anticipated, and let Kepler reach all of its design goals. That would have taken us through to 2017. Now, with Kepler potentially out of action, that means, and this backdrop of it not quite gathering the quality of data it expected in the time that it expected, its science goals will be significantly compromised if it turns out that it can't be revived. So, this is quite a lot of bad news for astronomers working on this subject. Earth-like planets will be there in the Kepler data. Remember that the Kepler data that's been taken up to the point of this problem has not all been reduced. It takes months to reduce the data and massage it and dig out these subtle signals. So true Earth-sized planets have already been discovered, and Earth-sized planets in Earth-like terrestrial zones are present in the data, even if Kepler gathers no more data from now on. But of course, getting the full census with small errors attached and getting, of course, a very large number of habitable near-Earth mass or near-Earth-sized planets, may not be achieved. So it may lose a factor of 2 in terms of just the body count of Earth-like planets that it finds if it gathers no more data. Still an incredible success, still has transformed the subject. And astronomers' attention, not just because of the Kepler problem, but just because this is one of the hottest games in science, has turned in the last months, in the last few years, really since Kepler's success, to the next step, which is characterizing these Earths. And that needs all pretty heavy-duty hardware. Kepler's a 1-meter telescope. That's tiny by modern astronomical standards. The next generation of missions that can follow up the Earths that are being found and to say what their atmospheres are made of, or look for even smaller planets, are going to cost multi-billions of dollars, and they'll involve substantially larger telescopes. The Europeans and NASA are working together on mission designs, but they're very fluid. None of these missions is funded. Some of them have been on the landscape for a decade, like the Terrestrial Planet Finder, and then were taken off the manifest because of no money for them, have been revived with different designs, and are now back in play. I don't think astrobiologists are going to give up on their goals, and the public is excited about this science, and I think even Congress is supportive because this is good stuff. And the United States is a world leader in this. So, you know, the big picture for astrobiology and exoplanet hunting and characterization, I think, is good, but this is more than a little bump in the road. It's kind of unfortunate news.
Our next question is from Julian. He asks, could you explain the fundamental plane relationship for galaxies?
Sure. The fundamental plane is a concept that started emerging in the 1970s and then became mature in the 1980s. So as people looked at the diversity of galaxies in the sky, originally classified in Hubble's tuning fork diagram, which turns out Hubble implied there was an evolutionary connection between spirals and ellipticals, and that hasn't played out the way he imagined. People looked at the diversity of galaxies in the universe, their structural properties, their kinematic properties, their stellar populations, and so on. And they wanted to find underlying relationships, underlying physical relationships that might, of course, explain how galaxies came to look the way they do. And as the quality of data improved, the 1970s and 1980s corresponded to CCD's maturing, and so the quality of galaxy data improved vastly in that time. People started to notice relationships between galaxies, that although spiral galaxies can be bigger and smaller, and ellipticals have a large size and mass range too, and spirals have different degrees of bulge population, which is the old stars near the center, and different types of winding of the spiral arms or prominence of the spiral arms. A lot of variations in galaxies. They can have warped disks or tilted disks or bars. Spirals have a diverse morphology. There were some underlying common features, and the fundamental plane was a simple way of trying to characterize galaxies in terms of a handful, just a couple of quantities that could encapsulate the full diversity of galaxy properties without getting into the gory detail. In other words, you know, don't get into the weeds and start worrying about the details of the shape of the spiral arms and how many H2 regions and the warp of the disk, but actually characterize their global properties. So their fundamental plane emerged originally for elliptical galaxies, which are the simplest galaxies to study since they essentially just have a pure old population of stars in elliptical orbits. They're simpler to characterize. Spirals have multiple stellar populations, but the fundamental plane is extended to spirals too. And the two core parameters that turned out to be useful in terms of characterizing a galaxy were the rotation speed of the stars in a particular region of the center, and that keys, because of Kepler's laws, to the mass of the galaxy, and the surface brightness of the galaxy, which is essentially the amount of intensity per unit area of sky within a particular physical region. So you can characterize the velocity of the stars in a particular central region of the galaxy, and then the amount of light in those stars in the central region of a galaxy. And it turned out that those quantities were related linearly, with some curvature actually, so not completely linearly. And then when people looked harder, they realized the fundamental plane was not as simple as a relationship between two quantities, but there were correlations with third and fourth quantities that were more subtle. But without getting into detail, because it's a complex subject with its own big literature, fundamental plane is a simple way of categorizing the complexity of galaxies in terms of a handful of quantities that describe their global properties. And as in the original goal of that research, the fundamental plane has guided theorists on how they think galaxies might have formed. For instance, with elliptical galaxies, the fundamental plane gave support to the idea that elliptical galaxies form fairly early in the universe by essentially gravitational freefall collapse. The fundamental plane was consistent with that kind of an evolutionary scenario or formation scenario.
All right, the next question is from Alice Amanda, and she asks, Could you say a little bit about the latest Planck results?
Planck is a worthy successor to WMAP. It's a European mission. Americans have involvement, though. Pretty much it's a worldwide mission, looking at all the investigators from a dozen or 15 countries. Planck was building on WMAP. WMAP carried out its mission for essentially a decade and made exquisite pictures of the microwave sky. So we're talking about missions that are there to understand the microwave background and tell us about the early universe, and in particular push our models of cosmology. Planck, it goes better than WMAP in two ways. One, in angular resolution, gets yet smaller details on the microwave sky down to a few arc minutes, and also in terms of sensitivity. So pushes down towards these very subtle features. Remember, all the features of the microwave sky, those classic maps you see from WMAP where the color scale goes from red to blue, the full variation from the reddest red speckles to the bluest blue speckles amounts to a few parts in 100,000 of temperature or intensity variations between those parts of the sky. Very, very subtle features. And they are not detected with very high significance at the level of the individual variations. So Planck is able to do better. I mean, not dramatically better. We're talking about a factor of 2 or 3 better, which is still worth having. Planck released its initial results, its first wave of data, and it immediately resulted in a tweaking of some of the cosmological parameters. So I've already talked about Lambda CDM. That's the standard cosmological model. And if you have that standard cosmological model, you also, and you tether it in microwave observations, because remember, the microwave sky is telling you what the universe was like when it was 1,000 times smaller than it is now. And then you have a lot of data to tell you what the universe is like now. So you can connect the dots between 400,000 years after the Big Bang and now, and make sure make sure the model predicts both what you see now and what you see in the microwave sky. So that's really how the science is done. Well, WMAPs gave us some cosmological parameters, and Planck altered them. It didn't prove WMAP wrong. It just meant that the error bars or the uncertainties of the Planck measurements were smaller than WMAP. And it turns out, the new Planck answers were within the sort of standard 2 sigma error bars of WMAP, so there's no disagreement. But Planck is refining these parameters. Our level of knowledge of some components like the curvature of the universe, the age of the universe, the amount of dark matter, the amount of dark energy, not all equally precise, but some of those are known now to a few percent. And in a slightly annoying aspect of this, the age of the universe changed by somewhat less than 100 million years, but that's enough to change one digit, the least significant digit in the age that all of us have been quoting for years because of WMAP. 13.7 billion years is now rounding up 13.8 billion. So all those things had to get changed. But it's a sign of progress that we are now arguing about that third decimal place in the age of the universe. That sounds like a detail, and in a sense it is. Nothing is dramatically altered in our view of cosmology by knowing the universe is very slightly older than we thought it was with slightly poorer data. What is exciting about Planck, and this is not nailed down by their first release data, but this is where they're heading, is that Planck is trying to look at the very fine details of the microwave, of the fluctuations on these small angular scales, to try and affirm a part of the cosmology that we call inflation. So the frontier of Big Bang cosmology is to be able to verify an idea called inflation. Inflation was developed as a theory in about 1980, 1981 by Alan Guth most notably, and a couple of Russian theorists around the same time. And it tries to explain the smoothness of the universe, the lack of topological defects and monopoles, and also the flatness of the universe in terms of a very early phase of exponential expansion. And by very early, we mean in the model 10 to the minus 33 to 10 to the minus 35 seconds after the Big Bang. So really when the universe was at the level of a quantum event. It's an extraordinary hypothesis, and it's actually quite mature because in 30 years, people have worked out the astrophysics of inflation as well as they can, and that those theoretical calculations do indeed say that the characteristic of microwave fluctuations should bear the imprint of inflation, in particular in terms of what is the power or amplitude of the fluctuations on different angular scales. And that now becomes a test of inflation, so reversing that logic. WMAP made a very first stab at trying to test inflation, and Planck already has improved substantially on it in terms of a test of inflation, and it's consistent with the theory. I'll make a slight caveat though, inflation is not really just one theory, it's a sort of suite of related theories. The reason being that we don't know what the actual mechanism, the detailed physical mechanism that caused this inflationary expansion was. It's associated